So when you look at steel, what the electricity you're doing, there's heat is certainly an element. You have to be at molten temperatures. Molten iron is in 1500 plus Celsius. But the big element is how do you convert iron oxide into iron? And that's where there's really 4 ways to do that. You need what they call a reducing agent. So historically, carbon has been the dominant one. But if you want to get rid of emissions, you need to eliminate that.
Today on the Clean Power Hour, decarbonizing the manufacture of steel and other metals. I'm Tim Montague, your host. Welcome to the Clean Power Hour. Please check out all of our content at cleanpowerhour.com. Please give us a rating and review on Apple and Spotify so that others can find this content. And please subscribe to us on YouTube. My guest today is Adam Rauwerdink. He is the Senior Vice President of Business Development for a company called Boston Metals. Welcome to the show, Adam.
Good morning, Tim. Welcome to, thanks for introducing us or inviting us to this show.
Excited to finally get this going, and it's heady days in clean tech and clean energy. Lots of good news coming out of the United States with the IRA, spurning onshoring and reshoring of manufacturing, and so I really look forward to diving into Boston Metals technology, which is quite unique, and the company has been around a while because this is somewhat rocket science. Unlike most of the other technologies that we host here on the show, I think you guys are up to something quite complicated. So tell us a little bit about yourself first, and then let's dive into Boston Metals.
Sure. So thanks for inviting us again. So I've been with Boston Metal for about 5 years now. My background is in the climate tech, clean tech space. Since around 2010, I worked for a number of energy storage companies, grid scale energy storage. And then in 2017, moved to a different sector within clean tech, over to decarbonizing steel and metals production. And I've been with Boston Metal since. I joined when it was a quite small company, fewer than 10 employees. Today, we're over 100 employees, raised several rounds of capital, which is one of my primary jobs. And also established partnerships and beginning to deploy the technology commercially. So excited to tell you about all that today.
Very good, very good. Well, let's just start at the top. You're a spinoff from MIT. Obviously, some big brains behind the technology. What is the basic technology, and why is the runway so long for bringing something like this to commercialization?
Sure. So the core technology, we call it molten oxide electrolysis, and at its core, it's really a platform technology to convert raw material feedstocks, iron ore or other oxides, how you find metal in nature, and to convert them into high purity molten metal products that can go downstream into all the end use products we use. There's the 3 words in there kind of describe the core elements. So molten oxide electrolysis. It's molten. It's a high temperature process. When we're producing steel, this is at 1600 degrees Celsius, 3000 Fahrenheit. We are using oxides as raw materials. So iron ore, the primary component in iron ore is iron oxide. You might know that as rust. Our process converts that into iron, and then it's an electrolytic process. So electricity is the only energy source for the process. And as you described, dig deeper into the technology. Because of that, you end up with some terms similar to batteries. There's an anode, there's a cathode, there's an electrolyte. But at its core, it's using electricity to convert iron ore into liquid iron, which can go downstream into any form of steel.
And for our listeners, make the distinction between this process and a more traditional process, which is much more carbon intensive. So, how do you compare the two?
Yeah, so the traditional steel mill today, so there globally 2 billion tons of steel made each year. That's about the Eiffel Tower, 250,000 times every year. 70% of that is made using a process called the blast furnace, which uses coal as the energy source. And coal has really been the dominant way to make steel since the Iron Age a few thousand years ago. And that's the process that you see today. But with 2 billion tons being made, for every ton of steel that's made with a blast furnace, you get about 2 tons of CO2. And that adds up to 8 to 10% of global carbon emissions, which is one of the big focuses behind Boston Metal is driving that to zero. But that's the incumbent process, is converting iron ore to liquid iron using coal, using carbon as the energy source.
And I've noticed that there are now companies that are, making green steel with hydrogen, for example, instead of coal as a thermal source of heat. But are there gradations of decarbonizing steel?
Yeah, so one of the first things, or the most prominent sources of low carbon steel today, or low emissions steel, low embodied emissions steel, is recycling. So the 70% comes from coal. The other 30% globally is recycling, remelting. You'll hear the term the electric arc furnace, an EAF, which is how you take chopped up cars and appliances, melt that, dilute out some of the contaminants, and then produce new grades of steel and new steel products. In the U.S. market, about 70% of the market is recycling for steel. So in terms of low emissions steel, that's the fastest and the most dominant route today. Where you go from there to fully decarbonize the industry, which is the goal of the steel makers by 2050, that's where you start to have to get into alternatives to that blast furnace route. We're certainly one of those that think can scale to the required levels. You're seeing some early work in using hydrogen, green hydrogen being the focus. There are some other, kind of interim solutions such as carbon capture that could be applied to some extent to reduce the emissions from an established blast furnace. But really, the big focus of the industry is how do you move from carbon as energy source to something else? And at the scale of steel, there's very few other energy sources that can apply. We certainly believe in direct electrification. You could also use electricity to make hydrogen and go that route as well. But we can talk about some of the benefits of direct electrification.
Talk about the cost. How do you measure the cost of manufacturing steel? Is it cost per ton or something like that? And then what is the holy grail? What is it that you are chasing so that when you enter the large scale commercialization market, you are cost competitive with traditional steel?
So if listeners are from the electricity sector, they'll know the term, levelized cost of energy. And you can use a very similar metric in steel. So a levelized cost of steel, which takes into account all the different consumables, the operating costs, and then also, a levelized form of the capital costs. So that's what we typically use as well to compare our MOE process with an integrated mill or with a hydrogen approach. On a pure cost basis, there are also supply chain and scalability issues you can consider. But when we look at our process, one of the key variables, since you're moving from coal to electricity, the source of that electricity and the price of that electricity is one of the key drivers. So when we look at how do you compete, leaving aside carbon taxes, green premiums for the moment, if you want to compete directly on cost, $30 to $40 per megawatt hour of electricity at that price point, by the end of this decade, we think we can compete directly with the incumbent.
Yeah, so that is a potential sticking point, right? You need large volumes of clean energy to make this process clean. And there are places, certainly, upstate New York, where there's lots of hydro, places in the Midwest or in Texas where there's lots of wind energy. Well, let's talk about the go-to-market. What is your strategy? How do you foresee, getting traction in the U.S.? And then let's talk about the international as well.
Yeah, so sticking within steel, it's certainly a global play. So 60 to 70% of steel is in the Asian markets. Some of the high growth markets that are forecast over the coming decades are markets like India, certainly parts of Africa that could grow. So when we look at deploying the technology, yes, we're US based today, and we may do our first plants in the US, but we are very much global in our focus for deploying and scaling the technology. We do have a subsidiary for higher value metals, for niobium, vanadium, manganese, other metals that are much higher cost, lower volume than steel, but higher cost than steel. That we have just deployed the first product for. And that's actually in Brazil to start that product. So we are global in focus with how we deploy the technology. But when it comes to steel, electricity is a key driver. So in terms of the early markets where we'll deploy the technology, it'll be regions where you have access to low cost, reliable, clean power. If you don't use clean power, you don't have, the full green steel benefit that you would get.
Yeah. And one of the challenges with that is that wind and solar are intermittent. I'm a huge proponent for wind and solar. Obviously, anybody who listens to the show knows this. I'm a solar developer, but you also need storage then in most places. But so where are those places in the United States that it becomes practical in the near term to generate green steel?
So how we approach this, so two parts to the question. So number one, just a quick look at our business model. So we will be a licensee of the technology. So we're not going to ultimately be a steel maker, but our customers, who will be the steel makers, having access to clean power is important to them. So it's certainly important to us. So we look at that both as we look at it globally, geographically. So there are regions where you have high prevalence of nuclear power or of hydro on the grid today, which are base load renewable assets. You then have other regions where you have lots of wind and solar mixed with a grid, or as energy storage and other solutions become more prominent, different ways to generate 24/7 clean power. And when we look at that globally, there we start to work with some of the big renewables developers who have that expertise in assembling those assets. So we've talked with many folks in the US, in Europe, and elsewhere about how to, but we would certainly really rely heavily on their expertise. But that's it's very similar to the tech companies trying to get 24/7 power for their data centers or many other applications. And just touching on hydrogen again, if you're going to do green hydrogen, which is the primary focus, you need about the same amount of power. So any of these solutions that are looking to take a high energy intensity industry like steel and convert that to electricity, it's going to be all about where do you have the power, and that will certainly change over time.
So I took a quick peek here at the Wikipedia page on iron and steel industries in the U.S., right? And it's a very consolidated market. There are two major manufacturers, U.S. Steel and Cleveland-Cliffs, and their facilities are the vast majority are in the Midwest or Pennsylvania, and then there's one outlier in Alabama. So it looks like there's an opportunity here in the Rust Belt, obviously, to perhaps retrofit. Does the technology bolt on to existing steel plants, or what is the preferred method for doing an installation?
Yeah, so when you look at the steel industry in the U.S., just to touch on that point first, if you look at the integrated side, which is the blast furnace, there's really kind of three major markets where those still exist for 30% of the market. The Cleveland area, the Pittsburgh area, and the Chicago area. When you get to the other side of the market, which in the U.S. 70% is recycling, there it's much more distributed, a lot of it in the South, as you said. Cleveland-Cliffs, U.S. Steel, Nucor, Steel Dynamics, those are the big players. As you look at deploying our technology, what the end product from our process is molten, high purity molten iron. And if you go to an integrated steel mill today, if you march down the product flow sheet, you take in coking coal, you convert that to coke. So you have a coke plant where you're drying that out. You take your iron ore, you sinter that or pelletize that, which is really putting it in a mechanical format. You go to a blast furnace, which makes something called pig iron, which is very high in carbon. You then go to a basic oxygen furnace where you blow in oxygen to burn off some of that carbon. And then you have a crude molten iron, molten steel product. What comes out of that basic oxygen furnace and what comes out of the MOE process are very similar. So everything downstream from there, which is the next process step, is called ladle metallurgy, which is kind of where you do your cooking. You add in different ingredients to get the right composition, manganese, chrome, vanadium. And then from there, you cast that, roll that into different shapes. So what our process does, it replaces all of those upstream processes going from iron ore to liquid iron. That's replaced with our process. Everything downstream from molten iron down is all of the established processes to adjust the composition and to roll and cast that into the required shape.
So it sounds like you really could just drop in one of your furnaces. You call it a furnace?
Yeah.
And replace an old coal burning furnace, and bada bing, bada boom, right?
Yeah, and it's modular, so you have the option to kind of scale up over time and add incremental capacity. So certainly our focus long-term is deploying plants. A typical steel mill today is 1 million, 2 million, 4 million tons of steel per year as a production capacity. Mm-hmm. we're designing a solution that can be deployed at the same scales and hundreds of those plants globally.
Yeah.
But we also have the opportunity to scale down to much smaller levels. That's what we're doing in Brazil, where you're making a few thousand tons per year.
And for a 1 million ton plant, how many gigawatts of electricity are we talking? Do you know?
So it's the target for us is right around 4 megawatt hours per ton. To convert that around, a 1 million ton per year steel plant will require about 500 megawatts of baseload demand.
Hey, everybody. Thanks for listening to the Clean Power Hour or viewing it on YouTube. We do have a great YouTube channel. If you're not subscribed, please go to cleanpower.group and hit that YouTube icon and subscribe to our channel. Of course, you can find all of our content on your favorite audio platform as well. So please give us a rating and a review. Back to the show. That's a big solar farm or a small wind farm, depending on. But sounds like it's totally doable. I mean, that's the beauty of the energy transition. We've been at this for 50 years. It's been happening quietly, and now that climate change has burst onto the scene, and everyone is noticing that it's real, and climate change has gone mainstream. Americans are aware of it in all regions of the United States now, which is a wonderful thing. The future is still very uncertain, but we have the technology to make the transition to a zero carbon or even carbon negative economy. There's, and the scale of the problem is very big. It's very important that energy professionals understand this. The economy is something like 40 gigatons, and then the atmosphere, where we've been dumping our carbon right for millennia, certainly hundreds of years since the Industrial Revolution, is 800 gigatons. So it's 20x the net zero economy. It's a both and. But what else should we talk about? What is you've launched a pilot in Brazil, making precious metals. What's the size of that project?
Yeah, so that's a very different scale, an earlier version of the technology, but much, much higher value per ton. So there we're deploying a first project that will produce several thousand tons per year. So compare that with steel, where it's millions of tons per year. Here we're building plants that are several thousand tons per year, but can generate very high profit, very high revenues per ton. You look at crude steel, it's 50 cents per kilogram. You look at some of these higher value metals, it's $30 or $40 per kilogram. So very, very different economics, very different production, but markets that are measured in thousands of tons and tens of thousands of tons rather than a billion or 2 billion tons.
Yeah, steel is one of the largest mass consumed items on Earth, right? I mean, by volume and weight. It's
yeah, you're right up there with cement and concrete and water and oil and all the other very high volume. And in terms of industrial emissions, the two that really get talked about are steel and then cement and concrete. And it's I've been in climate tech since 2010, when there was certainly the boom and the growth of energy storage, which is now mainstream. In the last couple of years, you've seen that really accelerate within steel. So it's been an exciting time to be in what is historically a very old and slow-moving industry, to really see it accelerate because of climate tech and the pressure that's coming from across the supply chain.
And what kind of a reception are you getting from manufacturers at this point?
Very strong, and it's changing rapidly. So when we did our last funding round, for example, we brought in two of the largest iron ore companies. We brought in, at the other end of the supply chain, BMW as an investor who wants green steel in their vehicles. You see similar, early demand from construction, from some of the tech companies, certainly from automotive, and then within the steel makers themselves, where a few years ago, very few of them had, just 5 years ago, very few had climate pledges. Now almost all of them have interim targets by 2030 and net zero targets by 2050, and that's global in terms of where you're seeing that. And that's just the last few years that those have been rolled out. So it's been a very big period of change in the last few years.
And what does the future hold for Boston Metal? You said you're 100 employees today?
Yeah, slightly over 100. Where we're going today is we have the target by 2025 to deploy our first demonstration plant for steel. We're For the high value business, we're breaking ground now in Brazil for that first deployment that will come online in a rolling basis. Again, it's a modular technology, so scaling up next year and in 2024. But for steel, the target is to have the first demonstration plant in 2025. Because it's modular, that first plant will be a few full-scale modules, but it really provides all the validation you need to then add modules and go up in scale. So the second half of the decade is when we really see the first full-scale commercial deployments of the technology.
And you said that your business model is to license the technology. Does that mean that you're going to actually own the asset, the furnace, or how does that work?
Yeah. So for the high value side, we will own and operate plants. We will be producing metals and selling them, marketing them directly, owning the projects. For steel, we will not. So for steel, we'll be there as a licensee. We'll license the design to steel makers or to engineering companies that will build the plants for a steel maker. There is some core components and anode technology that's key to the technology that we will manufacture and supply ourselves, but we won't own and operate steel plants, at least not in any near-term iteration of the Boston Metal business model.
But so when you think about scaling, you're building bigger machines in higher volume, and does that all happen in Boston, or are you ramping up some kind of manufacturing facility somewhere else?
Yeah, so the portion that will control the supply chain is that anode, and that we're sourcing our first location right now within the U.S., where we'll have that initial scale up. In terms of the rest of the process, the design is certainly key, and that's what we control. The components of one of these furnaces are very similar to existing components in the steel supply chain today. Bricks, refractory bricks, and shells and rectifiers for the electricity. So there we leverage existing supply chains. We certainly provide the designs and our own, package for assembling all those parts. But some of we don't need to create new supply chains or new manufacturing scales for those components.
And what is so hard about scaling the technology? Because obviously this is a difficult problem to solve.
Yeah, so it's, I can compare that. Well, I've never worked in the tech industry, but there with software, you certainly can iterate, millions of times, per second. I worked in energy storage where it was quite easy. Everything was at low temperature. You could bring things down to lab scale benches, portions of membranes, et cetera, and iterate still quite quickly. You still had to then prove long-term reliability and performance. But when you get into something like steel, we're running at 1600 degrees Celsius. And so that adds a number of variables that really limit how quickly you can iterate. And so that's one of the key learnings that we've had over the last several years is how to take a very large scale challenging problem and break it down into the core components and iterate as quickly as possible. So as you march through a tour of our facility, you'll see the technology at everywhere from lab scale where you're making grams of steel over the course of a day up to semi-industrial systems where you're making several hundred kilos per day. And then there's several iterations in between. But the focus of those is how do we, as quickly as possible, iterate on the technology and drive the technology maturity forward. But it's certainly a very different challenge than you'd have even in energy storage.
Yeah. We've had a slew of thermal companies on the show recently. A company called Nostromo, which makes HVAC equipment. Their technology is the opposite. They're using ice and cold storage. But Rondo Energy uses electric thermal resistance heat to make 1600 degree hot brick batteries. I don't know if you've noticed Rondo at all in the news. If I'm a steel manufacturer, Rondo's knocking on their door too, saying, hey, we have a low carbon solution for industrial heat. Is it a both and, or do you have a sense of how Boston, pencils compared to some of these other thermal clean, theoretically, just using clean electricity? That's the key here, is using clean electricity. But how does that landscape look to you?
Yeah, so when you look at steel, what the electricity you're doing, there's heat is certainly an element. You have to be at molten temperatures. Molten iron is in 1500 plus Celsius. But the big element is how do you convert iron oxide into iron. And that's where there's really 4 ways to do that. You need what they call a reducing agent. So historically, carbon has been the dominant one. But if you want to get rid of emissions, you need to eliminate that. Some of those high value metals use another metal, to aluminum, for example, to do the reduction. That just doesn't work with steel because of the scale. And then you're left with, to do the reduction from iron oxide to iron, you can use hydrogen or you can use electrons, and that's the source of us. So heat is part of it. In our process, though, the electricity is providing the heat and the reducing agent. The electron is doing that work, chemical work, to convert iron oxide, to split apart the iron and oxygen and make liquid iron. So that's how we look at the process and how we differentiate from the incumbent that uses carbon for that energy and heat.
And you mentioned carbon incentives. I'm not an expert on what the landscape is there, but if I'm a manufacturer making dirty steel today, traditional coal-based steel manufacturing, and I want to decarbonize my process, is there a carrot that I need to make that jump, to bridge the gap?
There's been quite a lot of activity in that as of late. So there's a few different elements to it. So just on from the standpoint of how do I define clean steel, or how do I measure where I'm at for emissions with my steel versus any other producer, there you're seeing groups like Responsible Steel that are coming out with, we're putting together the structures to actually reliably measure across steel makers what's the embodied carbon emissions for each ton of steel. So that's one side, just from the regulatory standpoint. You're seeing a tremendous amount of work on the supply chain side, on demand, and that's happening within industry. So the automotive industry has huge pledges to reach carbon neutral with their supply chains. Steel is a huge part of that. You're seeing similar interest from large construction companies to put low carbon steels, low emission steels into their projects. So that's driving the demand. You're seeing government work, such as the First Movers Coalition here in the U.S. We're pulling together some of those large buyers to make pledges. You're seeing, in public procurements, starting to measure the emissions in the concrete or in the steel and having that as part of the bidding process. You're also seeing in Europe, one of the new measures that's coming into place in the next couple of years is a carbon border adjustment. So if a ton of steel is imported across the border, it's going to be looking at what's the emissions associated with that ton of steel. And so that's one fashion to protect local producers as they make investments in these lower carbon solutions. And then from there, you can certainly get into the different, you can call it a green premium or a carbon tax in that side of the equation. But there's a number of different elements to the supply chain that are trying to tackle all the different parts of that.
And are there specific incentives in the IRA legislation that impacts this industry?
Everything for renewables is certainly, indirectly and directly benefiting, but the other element is, as we scale up and start to deploy, there's a lot of dollars in there for first deployments, industrial deployments of technology offices like the Clean Energy Demonstration Office, where larger scale funding for technologies that are ready to make that leap from proof of concept or a mid TRL level to the first commercial deployments. And so that's something we're taking a very close look at.
One of the things that I love to point out here on the show is the role of good government. So being that you have such strong academic roots, I assume that you along your journey have benefited from government grants. What is the status of your revenue from, the investor side versus, which is probably largely equity investors, I'm guessing, but talk about that landscape. How does the company get to where it is today? And, you're on the doorstep of scaling and really going mainstream.
Yeah. So if you look at our history, so the company founded right at the beginning of 2013, was very small from kind of that period until 2017, 2018. There was one small seed investment from a private investor, but mostly government grants at that point, smaller scale government grants, largely from the Department of Energy in the US to de-risk early elements of the technology. Our CEO joined in 2017. I joined just after him. And then in 2018, we did our first round of private capital. We've now done two. So in total, we've raised about 100 million. Most of that is now private capital. But the DOE played a key role in those early days of taking the technology level up to the point where the private investors could see the story and see the opportunity and see that the technology had taken those initial steps of being de-risked. When you start to talk about these larger scale grants for first deployments, there you can see the DOE potentially coming back into the picture. But to this point, relying on private investment for scale up, both past and present and future.
Mm-hmm. Gotcha. Well, what else should our listeners know? And before you say that, before you talk about other stuff, I guess, when can you see, large scale clean steel manufacture happening in the flesh in the U.S.?
So today it would be, all of the recycling. So there you're seeing the pledges to move from, maybe a recycled steel electricity driven process that's, just from grid energy, moving that to clean power through.
Yeah, there's no reason that couldn't be done today, of course.
So for us, though, it's the second half of this decade. So 2025, we're targeting the first industrial demonstration plant. It's then about a 3-year project cycle to go from, go on construction and permitting to a plant coming online. So second half of this decade is when we see, the first 1 million ton steel plant using our technology coming online. That could be in the U.S. That could also be anywhere on the globe where you have clean power, or both.
Gotcha. Well, what else do you want our listeners to know that we haven't touched on so far?
Well, I touched briefly on our high value business. We actually did a press release this morning as we're recording this, announcing that we broke ground on that project. So that's when we look at the revenue side, that's an important part of the overall picture on Boston Metal, that high value metals. And that's been there since even our earliest fundraising rounds as part of the story. And earlier to market, higher margin, lower ultimate volume, but an important part of the puzzle for Boston Metal. So that's a project that's now coming online. We own the land. We've got working through the permitting process and starting construction there, but that'll see our early revenues initially next year, have been really scaling up in 2024 and 2025 to support the business. So that's an important milestone for Boston Metal, is seeing that project come out of our labs and our development facilities and actually break ground on a commercial project.
Yeah, it's exciting. And how long will it take to bring that Brazilian project online?
So initial production next year, really the big scale up in 2024, and then finalizing in 2025. And that's the first phase of it. That's a business that will expand in Brazil, will also expand globally. There we are producing higher value metals. We're also working with a lot of waste streams as the feedstock. So taking a mining waste or a metallurgical waste and capturing value from that by extracting some of the key metals. So that's how that business will scale, and that's a feedstock that is available globally.
Yeah, you think about all the landfills in the U.S. and globally, and how they are treasure troves. If you have some technology for separating the good from the bad, a lot of good stuff in those landfills.
Absolutely, yeah, and that's where at the end of the day you still have to obey thermodynamics and everything else, but we can go a lot farther than some of the incumbent processes can in extracting those high value elements. So what is a waste today and is piling up, we can extract the high value components from that and generate, avoid new mining and generate quite a large profit for Boston Metal.
Very good. Well, check out all of our content at cleanpowerhour.com. Please give us a rating and a review, and reach out to me on LinkedIn, on the website, cleanpowerhour.com. Subscribe to us on YouTube. And Adam, how can our listeners reach you?
Go to our website, www.bostonmetal.com, or I'm Adam at bostonmetal.com, so you can reach me there as well.
Excellent. I'm Tim Montague. Let's grow solar and storage. Thank you so much.